Hello guys, now we will discuss a very important numerical in microwave communication systems. Consider a 300-meter long coaxial transmission line with air separating the inner and outer conductors, and the line having a characteristic impedance Z0 with a value of 75 ohm. So the total length is 300 meter and it is a coaxial line, and its Z0 characteristic impedance is 75 ohm. A voltage generator is connected to one end of the line. The generator produces a step voltage that rises from 0 to 40 volts with a rise time of less than 1 nanosecond, and the generator impedance is 250 ohm. So it produces a step wave. Step input means the input from 0 to unit step means input from 0 to 1. Here is the input from 0 to 40 volt within less than 1 nanosecond, so it's very fast. And the other end of the line is connected to the load impedance with the 20 ohm, so the 20 ohm is connected to the other end. Please provide the overall diagram of the system. So this will be the overall diagram. Here we have the source Vg, a step input, and then its impedance Zg, which is connected to the transmission line, and its total length is 300 meter, and the time which the signal will take from reaching for reaching from one end to the other end will be 300 meter over the speed of the signal, that is 3 into 10 per 8 meter per second. So this will be 1 microsecond. So the signal will reach from the this end to the other end within 1 microsecond. Okay, and then a load impedance is calculated here, and this is the distance. Here is L. Okay, now we will first calculate the V1 plus voltage, the voltage which is present at this input, at the input side. This is known as V plus, V1 plus. So V1 plus will be its equivalent circuit will be here. This is the equivalent circuit. We will apply the voltage divider rule here, which is V plus 1 is equal to V1 plus is equal to Z naught over Zg plus Z naught into Vg. This is a simple voltage divider rule of the circuit theory. Vg into Z naught over Zg plus Z naught, right? And then we have the deflection coefficients. At the generator side we will be having Zg minus Z naught over Zg plus Z naught, and at the load side we will be having ZL minus Z naught over ZL plus Z naught, and the values are 75 ohm Z naught, Vg is 40 volt, step input ZL is 20 ohm, and Zg is 250 ohm. For the time delay, find the time delay. So this will be the overall network diagram, how the system will be actually implemented. Okay, and the second part is find the time delay due to 300 meter line. This is the time it takes for the unit step voltage to go to the end of the line. So as I explained earlier, TD will be 300 meter, the length of the line divided by the speed, which is meter per second. So this meter they cancel out this meter, and second per second will go to the second. So it becomes 1 microsecond. Okay, next show a voltage bounce diagram up to 5t. Okay, 5t is one time constant, that is your one time 1t is equal to here we calculated that was 1 microsecond. So here you can see that this is a standard diagram, and this is a transmission line of length L, and its characteristic impedance is Z0, and here we can see that the signal at time t is equal to 0. This is your V1 plus. So this is V1 plus will travel to the other end in 1 microsecond, right? T is equal to 1 microsecond. Then it will be reflected, and after reflection it will go again to the generator side or center side, and it will after 2 microseconds this will be V1 plus multiplied by reflection coefficient at the load side. So this is your reflection coefficient at the load side multiplied by V1 plus, the incident wave. So this V1 plus will become V1 minus. V1 minus is the reflected wave, which is equal to V1 plus into tau L. and then after hitting here it will again be reflected. After 2 microseconds it will be again reflected, and now it will become V2 plus. What is V2 plus? It will be V1 plus multiplied by TL multiplied by this time constant. So this whole signal will be multiplied by this time constant. V1 plus tau L multiplied by the tau G, the reflection coefficient at the generator side. So now this will become V2 plus, and V2 plus will reach here in 3t. After reaching here it will be again reflected, and now this signal will be multiplied by its reflection coefficient, and it will be TL. So we will get V1 tau L tau G multiplied by tau L. So tau L and this tau L will become tau L square. Here we can see that V1 plus dot tau L square dot tau G. Now when it will reach here it will be reflected again, and this whole thing will be multiplied by the tau G. So it will become V1 plus, so V1 plus tau L square tau G multiplied by this tau G, and it will become V1 plus this reflection coefficient tau L square and tau G square, and after hitting this it will be again multiplied with the tau L. So this will become tau L cube and tau G. So I am explaining it again. Here it is V1 plus, V1 minus, V2 plus, V2 minus, V3 plus, V3 minus, and this is your T, that is 1 microsecond the time the signal will take from for reaching from this end starting at after length L. Okay, so this is how we will get T. Here is 0, T, 2T, 3T, 4T, 5T and 6T. Now you see the calculations here. V1 plus is equal to 40 multiplied by 75 over 250 plus 75 from the previous formula, this one formula, which is we are applying using these values, right? So 40 into 75 over 250 plus 75, that will be 9.23 volt, and we will now calculate the reflection coefficients tau G, Zg minus Z0, Z0, Zg plus Z0. So this is your 250 minus 75 over 250 plus 75, it is 0.538, and at the load side we will again calculate like ZL minus Z0 over ZL plus Z0, and it will be minus 0.58. Now V1 plus is 9.23 volt, this we calculated. Now we will calculate V1 minus, it will be V1 plus into tau L, 9.23 multiplied minus 0.58, it will be become this minus volt, and V2 plus will be equal to V1 plus tau L tau G. So we will multiply this term, which is V1 plus tau L with the tau G. So minus 5.35 multiplied by 0.538, we get this, and then we will multiply this thing with the tau G. Here this is your V2 plus, and if we multiply it with again tau L, because the signal is reflected from right to left, so minus 0.28 multiplied by tau L, this tau L. Okay, so this becomes tau L square. Okay, so it will be 1.67, and then we have tau L square Tg square, so 1.67 multiplied by 0.538, and now 0.9 volt multiplied by again TL, which is minus 0. So this is the how the voltage V1 minus, V2 plus, V2 minus, V3 plus and V3 minus and so on are calculated. Now calculate the values of the voltage and show the voltage variation at point 150 meter halfway along the line. So halfway along the line becomes this 150 meter. This is your total 300 meters and its half is 150 meters. So it will become here. This is the line of 150 meter. So this is the line of 150 meter. So here we will simply have here, this is 0.5t and this is 1.5t, and again this is 2.5t, 3.5t, 4.5t, 6.5t. so this here we will be, here we have 1t 0, so in between we have 0.5t, Here we have voltage plus 9.23, and here we will be having voltage, the sum of these two voltages, and here we will be having all the three the voltages sum, and here sum of all these voltages, and here sum of all these voltages, and similarly here sum of all these voltages. So at 0 microsecond we have 0 volt, 1.5 0.5 microsecond we will be having 9.23 volt. At 1.5 is somewhere here, 9.23 minus 5.53, we will have 3.88 volt, and then we will be having 2.5 volt here, which is the sum of all of these three voltages. So at 2.5 we'll be having 1 volt. This is here 2.5, the sum of this we will be having 1 volt. At 3.45 microsecond we'll be having the sum of all the previous ones, similarly 4.5 and 5.5. Now if we plot the variation at 150, so we can see that at 0 microsecond we have 0 volt, at 0.5 we have 9.23, at 1.5 we have 3.8. So simply plot this. So here this is 1 tau, 2 tau, 3 tau. Here this is 0.5 tau. Okay, at 0.5 tau or 0.5 microsecond we are having 9.23 volt. So 0.5 second we are having 9.23, and it remains constant up to 1.5. So 1.5. Okay, at 1.5 we are having 3.88. So here we are having 3.88, and it is up to 2.5. So this is your 2.5, and then we have 1 volt, and then again we have 2.67, and then 3.57, and then 3.046. So this is the your plot of variation at 150 meter. 150 meter is here, and one important concept is, again you can see that there is some like this. Here we have at 0 we have 0 volt, but at this point we have this one voltage V1 plus, V1 plus, and V1 plus. Here we have V1 plus, and then we have your, here we will be having V1 plus uh, tau L in plus 9.3. Like you can see here that V minus is V1 plus into tau L, and then V2 plus, your this is your V2 plus, which is this one multiplied by this, right? Okay, calculate the voltages and show the voltage variation at 300 meter as a function of time. Now VL is equal to VSS. This is your steady state voltages. After the steady state, what the system will become? At steady state it will be just 20 over 20 plus 250 into 40, that is 2.96 volt. So this is the standard formula using the circuit analysis, 20 over 20 plus 250. Here you can see that 20 over 20, that is your ZL over 20 plus 250. So Z naught is ignored in the steady state value. This is ignored. We simply have ZL over ZL plus into ZG into VG. Simple voltage divider rule. So this is 2.96. This is the steady state value. And now we have to show the values of voltages and voltage variation. This is very important here. So as I already explained, this is your V1 plus, and this is your V1 minus, this is your V2 plus, and this is your V2 minus, so on. And at different times we will be just adding these waves, okay, to calculate the total voltage at one point. So here at 0 microsecond we will have 0 volt. At 1 microsecond here we will be having 3.88, that is this voltage plus this voltage. So we will be having these voltages, sum of these two voltages at this point. At 3 microsecond we will be adding this plus this plus this plus this, okay, so this will be 2.67, and at 5 microsecond we will be adding all of these above. So at 0 time we have 0 volt, at 1 microsecond we have sum of these two voltages, at 3 microsecond we will be having sum of all 1 2 3 4 these folds, and at 5t we will be adding all of these 6 vectors, these 6 waves. So this is how we will be calculating the time and voltage. And now we will plot this 0 microsecond 1 3 5. So this is 1 tau, 3 tau, 5 tau. Here will the 0 volt 0, and at 1 tau we will have 3.88 up to 3 tau, and at 3 tau we have 2.67, and from 2.67 at 5 tau we will be having 3.04. So this is how we will be getting a converging voltage here, which is equal to 2.96 as we calculated here. So this will ultimately converge to 2.96 in between these two limits. Okay. Now we will come to the question 2, which is again a 100 meter long transmission line with air separating the inner and outer conductors and Z naught. So the values are given here, and this is the same diagram. Here we can see that the voltage is the generator produces a rectangular pulse with an amplitude of 100 volt, and pulse duration is 200 nanosecond. So this is a rectangular pulse. It is a rectangular pulse, and its time period is 200 nanosecond, right? Now this is the diagram like before, and these all are the formulas like before, and this is the time, which is now 100 meter over 3. So there is time will be less because the distance is less, so time is 12. This is 1/3 the distance. Previously the distance was 300 meter, now the distance is 100 meters. So we have here 0.33 microsecond, right? Now the voltage variation diagram will be like 0, 1t, 2t, 3t, 4t, 5t, 6t, 7t. So this is your V1 plus, V1 minus, V2 plus, V2 minus, V3 plus, V3 minus. So V1 plus is 66.7 volt. How we calculated this? We calculated through this formula, this one, V1 plus. Here you can see that the Tg at the generator side reflection coefficient will be Zg minus Z0 over Zg plus Z0. That is 25 minus 50, 25 plus 50, that is minus 0.33. And at the load side we have 200 load side minus Z0 over 200 plus this is your Z0, and this is 0.6. And V1 plus is 100 over 50 over 250, 25 plus 50, that is 66.7 volts. So this is our V plus. Here we will multiply it with the tau g, and we get V1 minus, and here we will multiply this V1 minus with the here we will multiply it with the tau L, and here we will multiply it with the tau G, and this we get the V2 plus. We again here we multiply it with the tau L, and we get this wave, and here we will multiply it with its reflection coefficient, and we get this voltage, and so on. Okay, so V1 plus and V1 minus is 66.7 multiplied by 0.6 tau L, 40 volt, and V2 plus will be 40 multiplied by minus 0.33, that is minus 13.92, and then it will be 0.6, and then we multiply it with minus 0.33, and then here again we multiply 0.6, we get this volt. So this is the voltages we are getting. Okay, now show a current bounce diagram for the pulse up to 5t. So here the question is about the current bounce diagram. To obtain a current bounce diagram from the voltage bounce diagram, we will multiply the forward traveling voltage, which is V1 plus, V2 plus, V3 plus by 1 over Z0, the characteristic impedance, and backward traveling voltage by minus 1 over Z0. So this is the method. The current bounce diagram is shown below. So what we will do here, like this is our diagram, and here you can see we will here the forward voltage, this is 66.7. we will simply divide it with the Z0. Z0 is 50, so you can calculate easily that 66.7 divided by 50 is 1.334. okay, similarly here we will multiply it by it minus 1 over 50. Here we will getting minus 0.8, and here we will multiply minus 13 over 2 by 1 over 50. We will be getting minus 0.264, and this minus 7.92, it will be multiplied by minus 1 over 50. We will getting 0.158. Similarly these two currents. Okay, and now we will write these I1 plus I1 minus I2 plus I2 minus I3 plus I3 minus, and show the pulse voltage variation. So this is this part is completed here. Now calculate and show the pulse voltage variation at a point the 50 meter halfway along the line as a function of time. So half wave is 50 meter, the half of the 100 meter, and again if it is 0.33, its half will be here. Similarly here it will be the half of this thing from this point. Similarly this is the half line. Okay, so here we will having 0 microsecond 0.165, that is the half of this here, and then we add 1t here, that is 1.5, 2.5, 3.5, 4.5, and here 45 to here 4.5, and here 5.5, 6.5. Okay, so this is your 0.165. Now add 1 here, 1t, which is 0.33 plus 0.16, this is 0.495. Add 1t, again add 1t, add 1t. We will be having here, here you can see that the voltage, what is the voltage here at this point, 66.7. So here 66.7, and at this point this one is the half point, that is 1.5t. We will be having this plus this, so it is 106.7. At this point we will be having this plus this plus this, so this is 93.5, and so on. Okay, so this is the plot of variation. At 0 second we have 0 volt, at 1.675, that is the half t, we'll be having 66.7 volt, and then after 1 t we'll be having 1067, and then after 1 t we will be having 93.5, and then 85.5, and then 88.19. so it is moving to the convergence. Okay, calculate and show the current variation at d50. So for the current variation we will draw the line which is 50 meter, and similarly we will add up all the things here. This is 0t, and this is 0.5t. Here we have 1.334, and one after 1t, that is 1.5t, we have 1.334 minus 0.8, and then at this point we will be adding these three, and at this point we will be adding 1 2 3 above the 3 points, and at this point, that is 4.5 t, we will be adding these above variations. So when you 1.334, 0.534, 0.27, 0.428, 0.48, 0.449. So this is how we will be getting the table. And at 0 we have 0 ampere, at 0.165 we have 1.334 ampere here. Okay, at again after 1t we will have 0.534, and after 1t we have 0.27, 0.428, 0.48, and 0.49, and now it is moving towards convergence. Okay, so this is how the voltage variations are working here. So I explain it again. At this point I will be having this voltage here at 0.5, 1.334. At this point I will be adding this and this. At this point I will be adding these threes, and at this point I will be adding these above all, and at this point I will be adding these all, and at this point I will be adding these three all. So this is how I will be getting this table. So thank you very much for listening.